All right, so we are going to start with lesson 14, converting rational numbers to decimals using long division. Okay. So lesson 14, converting rational numbers using long division. Okay. So question number 1, or example number 1, says using the division button on your calculator, explore various quotients of integers 1 through 11. Record your fraction representations and their corresponding decimal representations in the space below. So in this part here, you're going to sit there and you're going to just type in random fractions, okay, random decimals. So like you're going to do 1 divided by 2. You're going to do 2 divided by 3. You're going to do 3 divided by 5. You're going to do 7 divided by 9. You're going to do 9 divided by 11, okay. You're going to do 5 divided by 8. All right, just random numbers, and you're going to sit there and you're going to start to notice that there are basically 2 types of numbers that keep on popping up. Okay, you either get a terminating decimal or you're going to get a repeating decimal. Okay, these are the 2 types of decimals that you are more likely to see: terminating, okay, and repeating. All right, these are the decimals that you are more likely to see if you keep on popping them up. Okay, so keep on using your calculator, you keep on looking, you'll see more. So in the chart below, organize the fractions and their corresponding decimal representations listed in example 1 according to their type of decimal. Okay, so we are going to put terminating decimals here, okay, and we are going to put repeating decimals here. All right, now I know like 1/2 is a terminating decimal. It's 0 and 5/10. I know that 3/5 is a terminating decimal. It's 0 and 6/10. I know 5/8 is a terminating decimal. I believe it's 0.675, I think. Let's verify that real quick so we can all be on the same page. Well, it's not going to pop up for me. Well, I wish I had a calculator here. Let's see if there's a calculator in the tools. Math tools. And hey, there we go, calculator. Okay, so 5 divided by 8 equals 0.625. My bad, guys. So 5/8 is 0.625. Okay, then you've got numbers like 1/3, which is 0.3333 repeating. Then you've got like 2/3, which is 0.6666 repeating. And if you manage to put in something like 4/9, you would notice that it's 0.4444 repeating. Okay? So what do these fractions have in common? Well, I just told you. They all terminate. They stop. They end. They have a stopping point. They don't continue on and on and on, whereas the other column has our repeating fractions or our repeating decimals in them, okay? These are all fractions that have a repeating number, all right, like 3 or 6 or 4 or 5 or 7 or 1 or whatever it be. These continue on and on and on, and they have to be written as such. 0.3 with a repeating bar, 0.6 with a repeating bar, 0.4 with a repeating bar. That's how we can write these decimals without having to create a long stretch of other things we have to do. Okay? So let's continue on. All right, so using long division algorithm to find the decimal of a -3/4. Okay, so we got to zoom in here. Want to make sure we zoom in and we have plenty of space. So use the long division algorithm to find the decimal value of a -3/4. All right, so we already know that our answer is going to be negative, so I'm not going to sit there and worry about that. So I want to use the long division algorithm to figure out what 3/4 is as a decimal. Well, if you remember, the long division algorithm is the one that has the division sign like that. Okay, so we got 3 divided into 4. Oh, my bad. Look at there. Mr. Hale made a mistake. He wrote it wrong. So let's erase everything. So we're going to start again. All right, so our decimal value, again, we got a negative. So 3/4 written as a proper division problem is 3 divided by 4. Now, can 4 go into 3? No, it can't. That's the reason why we put a 0 there. Now we have to add our decimal down here and shoot it straight up so we don't forget about it. Then we add a 0. So now we're not dividing 4 into 3. We're dividing 4 into 30, okay? And 4 can go into 30 7 times. 7 times 4 is 28. Now we subtract. 30 divided by 28 is 2. Still not done. We got to add another 0 and drop it down. Can 4 go into 20? It can. It can go in 5 times. 5 times 4 is 20. 20 minus 20 is 0. So my decimal is 0 and 75 hundredths, or a negative 0.75. Okay? Now, it stays negative because that's what was expressed in the original problem of a negative 3/4. All right? Let's continue on down here at the bottom. All right, convert each rational number to its decimal form using long division. Again, if you notice, I've got a negative 7/8, so my answer is going to be negative. So I'm going to go ahead and stick the negative way over here. Now I need to do 7 divided by 8. 8 cannot go into 7, so I put a 0, add my decimal point, put a decimal point up here, add another 0. 8 can go into 70. Let's see, 8 times 6 is 48. It's not big enough. 8 times 7 is 56. Not big enough. 8 times 8 is 64. That is big enough. So we put an 8. 8 times 8 is 64. We subtract, we get 6. We have to add a 0, bring down a 0, so 0 there. Well, we know 8 times 7 is 56. So we do 56 here. We subtract, we get 4. We add another 0, and we shoot it down. Now I've got 40. 8 can go into 40 5 times. 5 times 8 is 40. 40 minus 40 is 0. So I am done. 0.875 is my final answer. So it's a negative 0.875. There is my answer for part A. Okay. Let's look at part B. 3 divided by 16. This is positive. So I'm not worrying about any negatives here. Now I'm just worried about the positive. They're just finding out what the answer is. So 3 divided by 16. Okay, well 16 can't go into 3, so that's a 0. We add our decimal, and we shoot it straight up so we don't forget. Add a 0. 16 can go into 30 one time. 1 times 16 is 16. 30 minus 16 is going to be 14. Now we add another 0, and we shoot it down. 140. 16 can go into 140. Let's see. 16 times 8 is going to be 48. Carry the 4. 8 times 1 is 1. 8 times 4 is 12, or 8 plus 4 is 12. So 128. I like that. So we're going to do 8. 8 times 16 is 128. We subtract, we get 12. Add another 0, shoot that down. Now we got 120. All right, so 16 times 5. 5 times 6 is 30. We get a 0. 5, we got to add a 3. 5 times 1 is 1, plus 3 is 80. That's not going to work. 16 times 7. 7 times 6 is 42. Put the 2 down here. Shoot the 4 back up. 7 times 1 is 1, plus 4 is 11. So we get 112. So we subtract 112, and we get 8. Okay. Well, we ain't done yet. Got to drop another 0 down here. 0. So now I've got 80. 16 can go into 80. Well, look at there. I made it. I actually ended up helping myself out. 16 times 5 is 80, so we know that 5 can go here. 5 times 16 is 80. 80 minus 80 is 0. So there's my answer. 3/16 is the same as 0.1875. That's equal to each other. And there's my answer right there. I'm done. So 3/16 using division, like that, gives me 0.1875. All right, let's continue on. Okay, this should be a short, easy lesson. We're doing things that we should remember to do. All right, now example number 4, converting rational numbers to decimals using long division again. So we're not done. We still got some work to do. Okay. Now, I'm hoping that after doing this for a little while, you're going to recognize certain fractions as being what we call repeating decimals. All the previous ones, those were terminating. They ended at a certain spot. If they terminate, that means they do not continue on after a certain decimal. All right, so now we've got a few problems here, and this is what we're going to be looking at for repeating. Use long division to find the decimal representation of 1/3. So 1 divided by 3. 3 cannot go into 1, it's 0. Make sure we add our decimals and add our decimals. Make sure we add our 0 there for 10. 3 can go into 10 3 times. 3 times 3 is 9. We subtract, we get 1. Add another 0, shoot it down, we get 10. 3 can go into 10 3 times. 3 times 3 is 9. We subtract, we get 1. Add another 0, shoot it down, we get 10. 3 can go into 10 3 times. 3 times 3 is 9. Do you notice how we are repeating the 1 every single time we subtract? Okay? This is because this decimal is repeating. This one will continue on and on and on. When you can notice a pattern is going to continue, you can stop dividing. There's no reason to keep going on and on and on afterwards. So 0.33333 is our decimal, or 0.3 repeating. Okay? All right, continuing on. All right, we got 4 problems down here at the bottom. All right, so we got calculated decimal values of the fraction below using long division. Express your answers using bars over the shortest sequence of repeating numbers. All right, so you got, if you notice, you got negatives in these 3 problems, so we know our answer is going to be negative. Okay, so our answers are going to be negative, so we just need to do the division real quick. 4 divided by 9. 9 cannot go into 4, so I'm going to make sure I add my 0, put a decimal place. 9 can go into 40 4 times. 4 times 9 is 36. We subtract, we get 4. Add another 0, shoot it down, we get 40. 9 can go into 40 4 times. 4 times 9 is 36. 36 minus 4, 40 minus 36 is 4 again. So if you start noticing that there's a pattern, then we can stop, okay? And no offense, but I already noticed the pattern of the 4s repeating over and over again, okay? So at this point, I know I'm done. There's nothing more I can do. So this is going to be a negative 0.4 repeating, okay? That's my answer right there. I know I'm done. I can't go any further because I noticed that there is a pattern. Sorry, I'm going to delete a little bit here, guys. Okay, I got to erase so I can have space down here at the bottom. All right, so the minute you recognize the pattern, stop. There's no point to continue dividing. You're just going to sit there and see the same numbers repeat over and over and over and over and over and over again. There's no reason for it, okay? All right. So remember, your answer here was negative 0.4 repeating. Now we've got a negative 1/11. Okay, 1 divided by 11. 11 cannot go into 1, we put a 0. Add our decimal, add another 0, put our decimal up here. 11 cannot go into 10, so we add another 0. Now we add our another 0 here. 11 can go into 100 9 times. 9 times 11 is 99. Subtract, I get 1. Okay, this looks like it could be a repeating one, so let's try it again. We add a 0, we shoot it down, we got 10. Well, remember, we had 10 right here. All right, so 11 cannot go into 10. It's 0 times. 0 times 11 is 0. So we add another 0 and shoot it down. We get 100. 9 times 11 is 99. So we subtract, we get 1. You remember, see how it repeats again? 1, 1, 1. The zeros are constantly repeating. So there's my repeating decimal right there. Okay? This would continue on 0, 9, 0, 9, 0, 9 over and over and over again. So my answer is a negative 0.09 with the 0 and 9 repeating. Those are the 2 numbers that repeat. It's not the 9. It's the 0 and 9. Since those 2 numbers are the ones that are repeating, those are the ones that get the bar over them. Remember that, okay? Whatever numbers are repeating, those are the numbers that have to be put with a bar above them. So negative 0.09. 0.9 is what repeats, so the bar goes above 0.9. All right? Let's come down here to C. 1/7, okay? All right, so we got lucky here. 1/7 is positive, so no worry about a decimal here. But now we just got to do our division. 1 divided by 7. 7 cannot go into 1, so we add a 0. We input our decimal points down, add a 0 underneath the house. 7 can go into 10 3 times. 3 times, oh, sorry. My bad. I'm not thinking right. Oof. That's what happens when you rush. Okay? It's not 3 that we're doing, okay? Whew. All right, so 7 can go into 10 one time. 1 times 7 is 7. We subtract, we get 3. Okay? We add a 0, we shoot it down, we get 30. Okay? 7 can go into 30 4 times. 4 times 7 is 28. We subtract, we get 2. We add a 0, we bring it down. Okay? 7 can go into 20 2 times. Okay? 2 times 14, or 2 times 7 is 14. We subtract, we get 6. We add a 0, we shoot it down, we get 60. 7 can go into 60 8 times. 8 times 7 is 56. We subtract, we get 4. We add a 0. Okay? 7 can go into 40 5 times. 5 times 7 is 35. We subtract, we get 5. Add a 0 and shoot it down. 7 can go into 50 7 times. 7 times 7 is 49. We subtract, we get 1. Add a 0, add it down. 7 can go into 10 1 time. 1 times 7 is 7. 10 minus 7 is 3. We add a 0, and we shoot it down. We get 30. 7 can go into 30 4 times. 4 times 7 is 28. And then I'm beginning to see that the process is repeating. Look, 1, 3, 2, 6, 4, 5, 1, 3, 2, 1, 3, 2, 1, 3, 2. The process is repeating. So that means that my repeating decimal is going to be the 142,857 part. Okay? So my answer is 0.14285. Of course, the 1 doesn't show up. Oh. All right, let's try this one again. All right. 0.142857 is what repeats. That's what the bar goes over. Okay? And that's your answer. I'm not going to do D, negative 5, 6. It's not worth we've already seen plenty of these examples. Okay? Let's see. Example 5. How do we determine whether a decimal representation of a quotient of 2 integers with the divisor not equal to 0 will terminate or repeat? Okay? Well, with a repeating, remember, with repeating decimals, with repeats, okay, the numbers have a pattern. So when we identify that pattern, we can determine that it repeats. Okay? There are numbers out there that will go on and on and on forever without a pattern. Okay? Pi, for example, 3.1415926, it doesn't repeat. It goes on and on again with a whole bunch of random numbers. So it does not repeat. That is not going to be a repeating decimal. Where with terminates, with numbers that terminate, okay, they stop. They stop at a certain number. Okay, so you need to remember that, all right? Repeating numbers will show a pattern. Terminating numbers will just stop at a certain number. They won't continue on and on and on. All right? Let's look at example 6. Eric and 4 of his friends are taking a trip across the New York State Thruway. They decide to split the cost of the tolls equally. If the total cost of the tolls is $8, how much will each person have to pay? Okay, they want to divide $8 evenly. Okay? Well, how many people are on the trip? Okay? We got Eric and his 4 friends. So that means there are 5 people. They want to take $8 and divide it equally amongst the 5 of them. Okay? So that's 8/5, or that's the same as 1 3/5. Okay? Now, I know that means each person's going to have to pay at least $1, but $1 in what? So we do 3 divided by 5. 5 cannot go into 3, so that's a 0. We add our decimals, both at the top and the bottom. Make that a 30. 5 can go into 30 6 times. 6 times 5 is 30. 30 minus 30 is 0, so it's got to be $1.60 each. Okay? Just before leaving on the trip, 2 of Eric's friends have a family emergency and cannot go. What is each person's share of the tolls now? So now, originally, we had 5 people on the trip, but 2 have to duck out. They cannot go. So that means I've got 3 people now. So that means I've got $8 being divided amongst 3 people, which is the same as saying 3 can go into 8. Ooh, my bad. 3 can go into 8 how many times? Okay? 3 can go into 8 2 times. Okay? So 3 goes into 8 2 times, so that's $2 and something per person. All right? Well, if 3 can go into 8 2 times, that's 3 times 2 is 6. That leaves me 2/3. Okay? Now, if I want to do this, 2 divided by 3, 3 can go into 2, but I can add a decimal and make it 3 into 20. 3 goes into 20 6 times. 6 times 3 is 18. We subtract. 20 divided by 18 is 2. Add a 0, drop it down, that's 20. 3 goes into 20 6 times. Again, we get 18 minus we get 2. We see a pattern of 2 showing up. So that means each person is going to have to pay approximately, okay, $2.66 repeating. Okay? So somebody's going to have to round up, and it would be approximately $2.67 per person to have to go to the tolls, okay? All right, and that would be the way that works out. Now, again, if you have any questions about this, just send me a message, and I'll be glad to help you guys out, okay? All right, problem sets. Fantastic, okay? I want you to do number 1 for homework tonight. All right, let's see. What else we got? And is that it? It's the only homework problem we got? Oh, Mr. Hale didn't go all the way. Actually, you know what? Yeah, just do number 1 tonight, and we will work on anything else we need tomorrow. So that's going to be the end of today's lesson, guys. I want you all to have yourselves a good evening, and I will see you all bright and early tomorrow. Okay?